So today, to reintroduce this, we're talking about springs and spring energy. I'm going to leave the PDF notes and the video lesson to be the main introduction, but I want to do just a tiny bit of it here. The force of a spring is proportional to the amount you stretch it. And if you want to compress a spring, then the spring is going to push back at you with an amount of force proportional to the amount of compression that you provide. So the potential energy of a spring is something that we can calculate. And it is U sub S is equal to minus the integral of Fs dxs. If you integrate a force through its distance, you get the work done by that force. And if you have a force that you can turn into potential energy instead of just calling it work, then you put a minus sign on it, and that is your potential energy calculation. So the integral of kx is 1/2 kx squared, and the minus sign that is part of the force cancels with the minus sign that is part of the potential energy calculation. So we find out that a spring stores a certain amount of energy. And technically, with any indefinite integral, there's a plus c at the end, but we just let c equals 0, and then we don't have to worry about it anymore. And how do we use this? Spring energy gets included as part of the overall mechanical energy of our object, just like gravity does. So here's the example I want to do. A 250 gram mass is on a 35-degree incline. And there is a kinetic friction coefficient of 0.4. And at the bottom, we're going to press this thing against a 300 Newton per meter spring, compressing the spring 7 centimeters. So this is like in a pinball machine. The ball is pushed back against a spring. Usually we pull the spring back, but it's basically the same thing. And then when released from rest, I want to know how far up the ramp the mass will go. And this might be similar to one of your homework problems. I haven't really taken a look at that since I assigned the homework last week, but it's a pretty good example for me to go through that includes spring energy and gravitational energy and friction energy. So let's start out by having a nice diagram of the situation. There's my incline at my 35-degree angle to the vertical, or 35 degrees to the horizontal, I should say. And here is my mass, M, and then I'm going to provide a little wall here for my spring to get compressed against. So there's my spring labeled with K. And the spring has a natural length. So when you put the spring against the wall and don't put anything there, the spring is going to have a certain length. So we're compressing the spring by 7 centimeters. That's this x sub s. So this is x sub s. And this, that's k. Of course, that is theta. That is m equals 0.25 kilograms, because mass always has to be in kilograms. And then to symbolize the rough surface, I'm just going to put like scribbles there. And this is mu k equals 0.4. So mu k is against there. So what kinds of energy are we going to have? We're going to have kinetic to consider. So that's k equals 1/2 mv squared. We're going to have gravitational energy. So that's u sub g equals mgy. We're going to have spring, which is u sub s equals 1/2 k x sub s squared. And then we're going to have friction. And friction is neither a k nor a u. Friction is work. Work due to friction is minus the force of friction times delta s. We'll call it the distance traveled. So let's see what we can calculate. So eventually this box is going to get up to this point here, and that distance it travels is our ultimate goal. We want to know the value of that distance. So let's think about kinetic. Kinetic is going to be 0 because our object starts from rest. Let's think about the final kinetic energy, because with kinetic and potential energy, we have an initial value and then we have a final value. So we're going to have k sub f is equal to 0, because when this thing goes up the ramp, in order to come back down, it's got to briefly come to a stop at the very top. Maybe the friction is enough to hold it stop. I don't know. I didn't calculate that. But I do know that at its maximum height, it's going to come to rest. So let's see what we can say about gravity. U sub g initial is, let's call that 0. Let's say that our object starts at the 0 point as far as gravity is concerned. And we're implying the initial y sub I is equal to 0. Now there's a homework question I think you have where you're dropping something onto a spring, and the easiest thing to do there is actually set the y equals 0 at the point where your object touches or contacts the spring. So that would be out here in this example where the x sub s becomes 0, but I'm setting this initial value to be y equals 0. So we have 3 points we might possibly care about. The very bottom when we've compressed the spring, this middle point where the spring lets go, and then this top point where our mass comes to rest. At the end, we're going to have UGF is MGYF, and we can relate this Y final to the variable we care about, this distance D, because there's this nice triangle with our theta and the distance d and the y final. So this is going to be 0.25 times 9.8 times sine of 35 degrees times d. And that's how the variable we want to solve for is going to make its way into the analysis. Actually, that's one place it's going to make its way into the analysis. So we know the initial gravity and we know the final gravity as a little bit of a formula. Let's do the spring. The spring energy is U sub S initial is 1/2 K XS initial squared. So that's just 1/2 times 300 times 0.07 squared, because the spring was initially compressed by 7 centimeters. And I have calculated that already. 1/2 times that squared. So this is 0.735 joules. And then U spring final is equal to 0, because the spring is not a factor anymore. Once the spring gets to its natural length, it stops pushing on the mass and lets go of the mass. So then the mass gets to take all of that energy that was released and hold it as kinetic energy. And then there's this one more, work due to friction is minus force of friction times delta S. And since we are sliding, our force of friction is mu K times the normal force. And our delta S is just our distance d that we care about here. And we know in the incline, the normal force is mg cosine theta, because we've done that several times already. So we can just put our 0.4 for friction coefficient times 0.25 for our mass, 9.8 for g, and then cosine 35 degrees, and then times d, because we don't know that distance yet. And then I just have to calculate that over here. Mass times g times cosine theta times friction coefficient. Yeah, I got all those in there. So this is minus 0.8028 d. All right. So now I know all about all my forms of energy, and I'm going to apply my general idea of conservation of energy or non-conservation of energy. Initial plus work equals final. So my initial energy is going to contain my initial plus my gravitational initial plus my spring initial plus, now we have my work due to friction equals kinetic final plus gravitational final plus spring final. So now I can fill in all these details. 0 plus 0 plus 0.735 minus 0.8028 D equals 0 plus, and then I need to multiply those out. So I need my mass times 9.8 times sine of that angle, 1.405. This number up here is 1.405 D. 1.405 D plus this spring energy is blue plus 0. So now I have an equation that says 0.735 minus 0.8028 D equals 1.405 D. And let's put the terms with our distance over on the other side. 0.735 is equal to 0.8028 D plus 1.405 D. So this is kind of a nice intuitive equation, or at least it can provide some intuition, because this is my starting energy on the left-hand side. And then the equation tells me where the energy goes. Part of the energy goes into friction. That's where the 0.8028 times D came from. And notice that the amount of energy friction takes up depends on how far we've slid along the surface. And then part of our energy goes to increasing the height of our object. And with that one also, the amount of energy of height, the mgy, is proportional to our distance. So then we can calculate the D value by taking our 0.735 and dividing it by the sum of those other two numbers. Oops. So factor out D here, and then divide by that total coefficient, and we find that D is equal to 0.333, which is 33.3 centimeters. So with this particular setup, we compress the spring by 7 centimeters at the bottom, and our object is going to shoot up diagonally by around 33 centimeters up the ramp. And while it does that, some of the energy is going to disappear into friction and turn into, our book calls it internal energy, I call it thermal energy. And some of that energy is going to be gravitational energy, ready to be released again, so the object will probably slide back down. So to recap, the initial energy was spring potential energy of 0.735 joules. And friction took an amount of energy, which was 0.8028 times D. So I can calculate that real quick. That times that. So that's 0.2 0.267 joules. And then the remaining energy is UG, gravitational energy, which is that times that 0.468 joules. And if we add these things up, 7 and 8 is 15, 1 and 6 is 7, and 6 is 13, so there's the 3, and then 1 and 2 is 3, and 4 is 7. So yes, they do add up. And that gravitational energy was proportional to the distance traveled up the plane. Now, one interesting thing is we could calculate the launch speed at the moment the mass left the spring. So to do that, we would do a similar calculation. We would do K initial plus UG initial plus US initial plus work final is equal to K final plus UG final plus U spring final. And this is 0. We could consider that to be 0. This is our 0.735. And this we could call minus 0.8028 d2 equals 1/2 mv2 squared plus 1.405 d2 plus 0. So all I've done is I've set the d value to a specific distance for this launch process. Up here in the diagram, I drew 3 dots for important locations of the mass, the very bottom, the point here at the middle where the spring lets go, and the point up here where the spring reaches, where the mass reaches maximum height. Well, we're now talking about this middle dot here. And at the location of this middle dot, we have released our spring energy. So the spring energy goes from 0.735 to 0. But we have lost some energy due to friction because the entire surface in this scenario was rough. So we're going to lose that amount of energy due to friction. That amount of energy is going to go into gravity. And we're basically going to have 0.735 minus 0.8028 times 0.07. That's the distance traveled between the very bottom and the point where the spring lets go. And then let's move this 1.405 times 0.07. D2 equals 0.07. Let's move that over to the left-hand side, and that gives us our K final, which is 1/2 mv2 squared. So how much energy is this? 0.735 minus 0.8028 times 0.07 minus 1.405 times 0.07 equals 0.5805. That is 1/2 times our mass times v squared. So then if we multiply both sides by 2 times 0.5805 divide by 0.25, that would be v squared, but I want plain v, so I'll just take the square root of it. So 2 times 0.5805 over 0.25 in the parentheses is 2.15 meters per second equals V2. I was calling it V2 for the second dot in the diagram. All right, so that was a nice, thorough example thinking about different points along the way with 4 different kinds of energy, kinetic, 2 kinds of potential, and then work due to friction, all in the same analysis. So if you guys put that together with the information in the PDF note and the video lesson, I think you'll have a pretty decent idea of how to do conservation of energy calculations.